This is lesson 2.1 for Algebra 2. We are discussing relations and functions. Our learning target is to identify functions and to evaluate them. So a relation is a set of pairs of input and output values. Our input values are the x-coordinates, and we call that the domain of the relation. Our y-coordinates represent the range or the output values. And there are four different ways that we can represent relations. We can list them as ordered pairs. We can list them as a mapping diagram where we describe how the different values are being connected. So in this case, the -3 is being paired with the 4. The 3 is being paired with a -1. 4 is being paired with -1. And 4 is also being paired with a 3. So it's the same thing we had listed as the ordered pairs, just in a different format. The other two types of ways we can represent relations would be with a table of values, or we could actually graph them. So understanding domain and range is important. We have different types. We have some where they're distinct points versus sometimes we have a whole graph with continuous lines or curves that represent an infinite number of points. For domain and range of discrete points, when you have distinct points and you're asked to find the domain and range, you simply list the specific x values for the domain, and then the specific y values would be your range. So in our first example here, it says when skydivers jump out of an airplane, they experience free fall. At 0 seconds, the skydiver is 10,000 feet above the ground. At 4 seconds, he is 9,744 feet. At 8 seconds, he is 8,976 feet. And at 12 seconds, he is at 7,696 feet. At 16 seconds, he's at 5,904 feet. So in the pictures here, we've shown you the four different ways that we could represent this information. We can show it as a mapping diagram, again, where we are pairing the input or the seconds with the output, his height. We can also represent them as ordered pairs. We can put it in a table of values, or we could plot those points. So in this case, we have specific points. Our domain would be all of our x values. So we're going to list our x's, 0, 0, 4, 8, 12, and 16. Our range, again, we're listing our y values for this, so we would put our output values, 10,000, 9,744, 8,976, 7,696, and 5,904. Typically, we would put those in order, so we could start with the 5,904 number. I've listed them this way just so that you can see how they were being paired up. It wouldn't be wrong to not have them in order. It's just a little easier to see if you've missed any if you do have them in order. If we have a continuous graph and we're asked to find the domain and range, we are going to use an inequality to represent those. For example, we might say something like x has to be less than 3 or y has to be greater than or equal to 0. Our hint for you is to look for a unique point that creates a max or min value for x or y and describe the domain and range from that point. If the graph continues on in both directions forever, this means that x or y can take on any value. We label this as all real numbers. So let's look at our few examples here. In our first one, we have a line. It goes on forever because we have these arrows here. So there's no cutoff for x's or y's. We would say x equals all real numbers. And again, we could write that as a capital R with a double bar. Our range, so this was domain, and our range, there's no cutoff as well. So we would say y equals all real numbers. Or again, we could say y equals that capital R. With our second picture, notice that we do have a cutoff. We kind of stop here. Our line This looks like an absolute value graph, a V-shaped graph. So our graph continues upwards forever, but it has a cutoff down here. All right, it's not going to go below that point. When we talk about vertical changes, we are describing the range. Horizontal is describing our x's or our domain values. So in this case, if we continued on forever, we are going to end up using these x values to get up to those points. So our x would be all reals, our domain. Again, we can say this. Our range, though, for this one, we have a cutoff. The lowest value that our y value gets to is down here at looks like -4. So we would say that our range is y has to be greater than or equal to -4. We can't go below that, but we can be anything going higher. So all of these y values above it are getting used to get over to this point. For our third picture, notice that it is being cut off in all directions. Our x's, we are breaking it here and here. So we would say for a domain that our x's are somewhere ranging, sorry, I shouldn't use the word range for that. Our values go from somewhere between a -6 over here to a +6 there. So we can say that x has to be greater than or equal to -6 and at the same time less than or equal to +6. All of these x values are getting used to create that ellipse. All right, looking at the y values, our range. Now we are cutting it off here and here. So we are going for y's somewhere in between a -2 up to a +2. All right, so once again, if you're looking at domain and range of discrete points, like we had in our skydiver example, then we just list the individual values. If we have a graph where we have an infinite number of points, then we list them with inequalities. So a function is a specific kind of relation. It's a relation where each element in the domains, your x's, correspond to exactly one element in the range, the y's. So let's take a look at some of these mapping diagrams to see which of these would be functions. So a function cannot have an input going to two different outputs. Every x has to be paired with a single y. So look at our first example. Our 2 is paired with a 1. Okay? That's the only value paired with a 2. The 4 is being paired with a 1. That's the only value being paired with 4. And our -5 is being paired with a -3. Again, that's the only pairing, so this is a function. In our second picture, again, based on the arrows, every one of our x's is just being paired with a single y, so this would also be a function. But notice in this third mapping diagram that our 1 here is being paired, sorry, my board's off just a little bit here. Our 1 here is being paired with two different values, and that's what we said can't happen. So this is not a function. It's still a relation, it's a mapping diagram of a relation, but it doesn't fit the criteria to be a function. If we're given a list of points, this means that each point should have a different x. There should be no repeats. So all of our x's have to be unique. Here we have a 4, 8, 1, 6, 4. Notice here and here, our 4 value for x is being paired with two different y's. So that makes this not a function. Looking at the second example, our x's, we have a -7, a 9, a 14, a +7. Those are all different. We do have some repeats for our y's, but that's okay. We're just focusing on the x's, they can't repeat. So this is a function. If we have a graph instead of individual points listed, we can use something called the vertical line test. You might want to highlight this. This is an important vertical line test. It determines if something is a function. So what we do is we look at a vertical line that goes through our graph. It cannot touch more than one point at a time. So if you draw a vertical line and it hits two different points on your graph, then it's not a function. So looking at our first example here, notice right here we have two dots that are lined up vertically. So if I tried to draw a line through those, I'd hit two spots at once. So not a function. And if you're asked for a reason, we would say fails vertical line test. All right, our second example, we can look at dropping vertical lines through here. At any one time, our vertical line only hits one dot. All right, so this would be a function, and we would say it passes our vertical line test. Our second example looks similar to our third example looks similar to our first one. However, our dots, if you look at them, our points are all separated. None of them line up vertically. So we would say this is a function, and it passes our vertical line test. Our last example here, if we drop a vertical line through, notice that it hits in two spots at the same vertical line. This would not be a function. And again, our reason would be fails vertical line test. All right, so there are two ways we can represent functions. One is a function rule, and one is function notation. So on the left, we have a function rule. It's a typical equation. This one's a linear equation, y equals mx plus b kind of format. Our function notation looks like this. And this notation is read f of x. Many students think of it as f times x. That is not the case. All right, we are not multiplying the f with the x. Typically, when we use parentheses, it indicates multiplication, but this is different. This is called function notation. So f of 2 is basically just saying find the value of your function when x is 2. So if we take our function, it was 3 times something plus 2, and they are telling me that they want me to put a 2 in there. Okay, that's what this is indicating. Find the value of the function when x is 2. So I put a 2 in for x. 3 times 2 is 6. 6 plus 2 would be 8. So f of 2 is 8. That is one way of saying the same thing as this ordered pair. You put a 2 in for x, and we got an 8 for y. Okay, just a different type of notation. So looking at our next example, g of x equals x squared plus 5x minus 3. They are asking us to evaluate when x is negative 1. We want to find the value of g, which is this function, when x is negative 1. So we're going to put a negative 1 in there. Be careful here. We're squaring a negative 1, which comes out as a positive 1. 5 times negative 1 would be negative 5. And then we are, subtracting 3. One minus 5 would be negative 4. Subtracting 3 more would be negative 7. So we could say g of negative 1 equals negative 7. Go ahead and pause the video and you try this next one. All right, plugging in a negative 7 for our x, and then simplifying. Negative 7 plus 1 would be negative 6. Its absolute value would be positive 6, minus a 5 equals a 1. So we could say h of negative 7 equals 1. Function notation can also be useful when we're interpreting graphs. Given this graph, they're asking us to find f of 0. That means find the value of our function. Find y when x is 0. So we're going to go to x being 0, which is right on the y-axis. X being 0, we look up and we say our value for y is 1. So f of 0 would just be a 1. The second question says, what is x if f of x, or y, is equal to -1? So we want our function to have a value of -1, and we're looking for the x value when that happens. So now we are looking here for y being -1, and we go across and say, okay, where is that x value? And that x value is at -2. So we would say x equals -2, or f of -2 gave us the -1. The value of our function at -2 gave us an answer of -1. So when trying to write a function rule for a real-world problem, we need to determine which variable is dependent and which is independent. Our dependent variable is going to be our y value. Our independent value is our x. Okay, so independent is x, dependent is y, because y is going to depend on what we dump in for x. So here it says a pizza costs $14 with a flat delivery fee of $1.50. What function rule models the total cost of the number of pizzas delivered? So what we have to determine is, does the cost of the pizza, the total cost, is that dependent on how many pizzas we buy, or is the number of pizzas we buy dependent on the total cost? And in this case, it makes more sense to say total cost is dependent on the number of pizzas we order. Okay, so I'm going to let x equal the number of pizzas, and y is going to be my total cost. Okay, so x is the dependent, sorry, x is the independent, y is the dependent. Total cost depends on the number of pizzas. So let's represent our total cost. It says it's $14 for every pizza, and we have a flat delivery fee of $1.50. So we're going to spend $14 for each of our pizzas that we buy, plus we're going to pay an extra $1.50 for them to deliver. Okay? Now, we want to write a function rule for this, so I'm going to change that y into f of x. Okay? It's just saying that my function is dependent on x. Okay? So now if I want to evaluate for 5 pizzas, I can say, well, what is f of 5? If I order 5 pizzas, I'm going to plug that in. 14 times 5 would be 70, plus $1.50. We'd be spending $71.50 to buy those pizzas. Okay, go ahead and pause the video for a second and try this last question here. All right, let's check our last question. It says you are buying bottles of sports drink for a softball team. Each bottle costs $1.19. What function rule models the total cost of a purchase? All right, so our function rule, let's let cost, we'll use a C for total cost. Okay, and let's let B represent the number of bottles. Okay, so our total cost is based on the number of bottles of sports drink that we get. We're going to spend $1.19 for every bottle. Okay, so that would be a function rule. If we wanted function notation, we could say cost is dependent on the number of bottles. So instead of just a C, we could say C of B. Okay, evaluate the function for 15 bottles. So what is the value of my expression if I put in 15 for the number of bottles? So if you took $1.19 times 15, you should get $17.85. Okay? All right, you guys will be going and doing the assignment for 2.1. It is a worksheet. Thank you.